Okay, welcome to this second lecture of week 4, where we will talk about solutions to forced differential equations and how to generalize that to a state space system or a vector differential equation or general state space of n dimensional systems modeled by x dot is a x plus bu. Let us start with a linear system. X dot equal to a x for the moment. Well, let us leave out b, and what we had last time was that the state transition matrix starting at time t equal to at the initial time t not equal to 0 was given by e power a t, right. And then so we said that the solution x of t is simply phi of t times x naught. Okay. So this gets us to the next set of questions that we should answer, that again would be very instrumental in deriving future results in this course on controllability and observability and related concepts. So what happens when u is not equal to 0 and u is, well, it may not necessarily be a constant, but it can also be time varying. Okay, so as usual, just to make things a little easier, we will start with a univariate or even so called as a scalar system. Okay, so I just say x dot equal to a x plus bu, and finding solutions is as usual, again integrating the system. Okay, so just keeping in mind or just following some of the tricks that we used to solve equations of this kind, let us say I multiply both sides by e power minus a t and do all the relevant steps. So I will just skip all this, skip reading all these steps. It is very self explanatory. So by doing all this, it implies that x of t is e power a t x naught. This is again the solution to the unforced system, plus an extra term now which comes because of the input at b a t minus tau, e power a t minus tau, b u tau and d tau. Okay. So this is again something which we can kind of compute by using some kind of intuition that we know from our earlier courses in calculus. Okay, and that is what happened in the example that we also checked earlier, right. You can use this method or even directly of how we computed by using Laplace transforms, for example. Okay, so following these similar steps, now can we show that the solution of an LTI system where x is now n dimensional state vector is given by this particular expression, or equivalently, since I can just get this e power a t outside, and that the equation looks something like this, or in general if I were to write it as a state transition matrix phi of t, then the expression would look something like this. Okay. So let us see if this is actually true. So where do I start from? I start from okay, there is some rule which I will use in the proof. I start from x dot is a x plus bu. Again, just for simplicity, or just still the beginning of this lecture. So we will just again look at time invariant case, and we will explicitly deal with the time varying case in the next lecture. Okay, so what do I propose as a solution to this set of equations is the following: x of t, I will write it in a bit of a general form, is phi of t x naught plus phi of t integral 0 to t, I have phi minus tau b u tau and d tau. Okay, now the question is, let me call this equation number 2, and just to say verify that this is a solution to the differential equation labeled as 2. Okay. So, how do we satisfy, how do I verify this? First, check initial conditions. Okay. So, what happens at t equal to 0? T equal to 0. So, on the left hand side I have x of 0, here I have phi of 0 times x naught, which is the initial condition, plus integral. So, again phi of 0, integral from 0 to 0 and blah 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 in the integral. So, the reason I do not write anything here is because I am just integrating from 0 to 0. So, this term will vanish and I am just left with x naught. Okay. So, the initial conditions are fine. Okay. Now, the second thing is does, so first is verify the initial conditions, and second, now does this x of t satisfy the differential equation 2. Okay. So, I just differentiate this, okay, and put it back. So, I have so the first term phi dot of t x naught plus d over dt 0 to t, okay, I will just get this inside for a while, phi of t minus tau b u tau d tau. Okay. So, the first term x dot is phi of t, I know is a times phi of t with x naught plus, okay. Now, I have a strange looking expression here, right, which I want to differentiate with an integral sign. So, I just use the Leibniz integral rule, right, which we possibly would remember from some of our earlier courses. Okay. So, I have a function here, you know, f x comma t integrating from a of x till b of x, and then the formula is given by this one. Okay. So, let us start with this, right. So, yes, I am just concentrating on the right hand side on this term which is differentiation with the integral sign here. Okay. So, the first term will be okay, you have a d over dt of t. So, this is my bx. So, let us just write down for simplicity what is. So, b of x is my t, a of x is 0, f of x comma t is phi t minus tau b u tau. So, this will be phi of t minus t b u t. Okay. So, this is what the first expression will look like. The second expression a is 0. So, this will not come into our case, and the third term would be the integral of again some 0 to t d over dt of whatever is inside phi t minus tau b u tau d tau. So, this is equal to, so this just this term inside the integral. So, what is, okay, what is the first term here? So, dt by dt is 1, phi of t minus t is the identity. So, I am just left with b u of t, right. So, this term here, this is the simplification of the first term here. Second term is 0, and I am looking now at the third term. So, the third term would simplify to, okay, d over dt of phi t, this will be a phi t minus tau integral 0 to t b u tau d tau. Okay. So, let me again write this again. So, what we have so far, so x dot, so sorry, am just differentiating these terms. So, what do I have here? So, I have A phi of t x naught plus b u t plus, then what is the remaining term here. So, I have integral 0 to t a phi t minus tau Okay, so I can rearrange these terms as a phi of t x naught plus 0 to t phi t minus tau b u tau d tau plus b times u t. Okay. Now, what is inside here? Phi t x naught plus this term in the integral. This is exactly the solution that I am proposing here, right, this one. Okay. And therefore, I verify two conditions here, that my solution satisfies the initial condition, it also satisfies the differential equation labeled as 2, and therefore, this expression here is a solution to x dot equal to a x plus b u. Again, I use the notation phi because I will use so this will be easier when I even use the same notation for linear time varying systems, whereas just as a little exercise you can do the same proof verifying the initial conditions and the differential equation for a specific type of state transition matrix, that is e power a t, which is valid for LTI systems. Okay, so once I know this, I can compute what is x of t. Not only that, if I have the expression for output, where maybe y could be some p-dimensional vector and then c and d being of appropriate dimensions, y can be computed once I know the value or the solution to x. Okay. So, again I just take a simple example and I just maybe compute for u equal to 5. I just keep the steps, right. I mean, they are written down very neatly here, and you can just write it down for yourself and verify. It's just an exercise, some mechanical laborious exercise. So, I will just skip reading this example. If you have any questions, you could always post them on the forum. Okay, so so before we conclude this lecture, we just do a little introduction to discrete time system. So, as said in the equation, so again x will be a n dimensional vector and so on. A, B, C and D will be the same kind of matrices that were in the continuous time system. So, what is the aim here, right? So, if what does it mean by even finding solutions? The aim is, so given an initial condition x0 and control signals u till k minus 1, can I find xk and yk, right, the state or the solution to this differential equation. Okay, it turns out to be simpler. I will just write down these steps and so much of this should be like very obvious to us. So, I have x k is a x k, again I am assuming that a and b are constant, even though we will in the next lecture maybe look at time varying case. Okay. So, given is certain initial condition x naught. Okay. Given x naught, okay, so how can I find x1? x1 is a x naught plus b u naught. Okay. Similarly, x2 is a x1 plus b u1. Okay, what is x1? x 1 is x naught plus b u naught plus b u 1. Okay. Sorry, there will be a here, right, and therefore, so I will have a square term depending on x naught. So, to compute x 2 I need x naught, I need the input at 0 and I need the input at 1. So, that is what is this statements mean, right. Given an initial condition x naught and given u naught till u k minus 1, can I find x k and y k. So, that is the reason I need information on this also, right. Similarly, to compute x 3 I need x naught, I need u at 0, u at 1 and u at 2, and generally for if I were to compute the value of state at any time k. Okay, as usual, similar to the continuous time case, these equations will also have a natural response and a force response. So, if I look at it closely, so if I just keep on doing this and say for instance, or for example, to begin with, assume u equal to 0, I am left with an equation which is like this: x at k is a, well, I just use the suffix k just to denote that it is a discrete time system x naught. And this a power k will now be my state transition matrix for the discrete time case. Okay, and then I can write it in general way as this form. Okay, again the state transition matrix will be, okay, given certain initial condition, what will my state be at say some arbitrary time k equal to 5 or 6 or whatever. Okay. Now, again similar exercise, how do we compute this matrix A power k? Is it always easy to multiply the matrix n times? Well, similarly to what we have in the continuous time domain of Laplace transform, we have now a powerful tool called the Z transform, and as usual I just start with a difference equation, convert it into the Z domain and then bring it back via the inverse Z transform to my discrete time domain. Again, the steps I will skip, very similar to what we did in the case of the Laplace domain for solving continuous differential equations. Okay. So, I will so skip a bit of these steps. They are very you can just write down and check for yourself. They are pretty straightforward to verify. Even an example, right? So, you can just work this example out for yourself. It's again everything is neatly written down in the slides, and you can just verify things for yourself. Okay. So, there are a couple of examples here which will help you understand how we compute it in discrete time. So, this will be a little useful in the later part of why we are actually doing discrete time systems. Much of the literature of today on networks, science related concepts in control, they work with discrete time systems for obvious reasons, which we will have, if we have time, we will touch upon those kind of models a little later in the course, when we have a decent amount of understanding of controllability and related stuff. Okay. So, I will again leave these computations, and again the kind of properties that we have here are again easy to verify of the state transition matrix, very similar to what we had earlier. So, this is easy to verify, this is easy to verify, this is easy to verify, and so on. Of course, these come from the continuous time case. So, we will end this lecture here with having learned how to compute force response of n-dimensional LTI systems, both for the continuous time and discrete time. So, the next lecture we will focus on time varying systems, where we can also maybe find a little proof for why we started off finding an equivalence between the vector differential equation and the matrix differential equation, and why we had assumed that solution to the matrix differential equation has direct implications on the solution of the vector differential equation x dot equal to Ax. So, that we will do in the next lecture. Thank you.